Ladies and gentlemen, please welcome Sebastian Merkel.
Is the microphone on? Yeah. Okay, so welcome back to this very special Centennial session. We are all celebrating the 100 years of the American Geophysical Union. And so we have a day on the Earth's interior, and we spoke about the differentiation in the morning, and now and the Earth's core, and now we're going to move on to more like the Earth like it is today, and how it evolved to what it is, so as the mantle, the core, and how you can observe it from different parts of the Earth. And so our speakers will be Linda Elkin-Stanton, Bruce Buffett, Jessica Irving, Hitoshi Kawakatsu, Anne Tavai, and Clint Conrad. And with that, I think Linda can come up on stage, and she'll be our first speaker.
Thank you. Thank you very much for this opportunity, and so lovely to see you all here today, and AGU shining with its centennial. I know a lot of people worked really hard for this, and I'm glad that we're doing this. I'm going to kick off this session on the initial conditions of the young solid Earth irresistibly by talking about magma oceans. And so I want to start with my conclusions. That's always a good thing to do, to tell people where we're going, right? And so I posit on behalf of our speakers today that Earth's initial conditions are set by magma ocean processes. And magma ocean solidification rapidly produces three key things for the initial Earth. One is a stable mantle, not a wildly convecting hot mantle as used to be thought, but a stable mantle with an oxidized upper mantle and a dense atmosphere. And so that's where I'm going with this little discussion. And here's a picture. It's a version, perhaps, of the ones that we saw a little in the earlier sessions with Sarah Stewart and others. The idea being that each really giant accretionary impact gives enough energy to the young Earth to cause it to be molten throughout much, if not all, of its mantle. And in the spirit of going back into history, Anat Shahar kicked us off this morning with a fantastic look back at the centennial of AGU, but I'm going to look a little bit further back to 1693. As far as I know, Leibniz was actually the first person to suggest that the Earth was once molten, suggest based on physics, some sort of modern physics. And I love to show this picture of his book because, frankly, it's illegible, and I'm quite amazed that anybody could get anything from it. But he was, when he wasn't fighting with Newton over calculus, his day job was keeping water out of the silver mines in the mountains of Germany. And he noticed when he went down into the mine that it was warm, and when he came back up into the surface, it was cold. And with just that information that all of us have, he immediately thought of a sphere radiating into space and losing its interior heat. And therefore, if you go back in time, the Earth was hotter. And if you go back far enough, it was probably molten. And later, Fourier was inspired by this book to work on heat transfer. And so the magma ocean was a primary idea long before Sasolov and Abe and the others, Solomatov, who've worked on this so extensively. The fundamental idea of a magma ocean is shown here in this little schematic wedge, where the convecting liquid mantle, here I'm showing a whole mantle magma ocean. It has a cooling upper boundary against the young atmosphere, and it has focused downwellings that solidify with the effective pressure as they pass across their solidus and delivers solid material to the bottom of that molten magma ocean. Now, it's possible that there would be an interior septum partway down in the mantle, closer to the core, where minerals would rise to the septum and then above that fall to the septum. But for the purposes of the sort of first order effects that I'm talking about today, that is not critical. There's degassing, perhaps continuous, perhaps catastrophic, into a young atmosphere, heat transfer out into space. And very importantly, we're going to have some discussions about the core later in this session. There is some kind of ongoing communications with the core, not just of energy, but also of composition. Now, when is this happening? It's true that the accretion talks first and then the core talks second. It's possible that my talk is a little bit overlapping in the time frame of our solar system. If you look far back on the left of this timeline, at 4.568 billion years, that's the oldest calcium aluminum inclusion, the little pebble pieces of oldest solid material from our protoplanetary disk in our solar system. And then you look way over on the right to the present day where we're standing. And of course, in between, life arises and it complexifies, and then we're able to measure extinctions. But we're sticking way on the left-hand side of this timeline. You see the blue dependent, almost like a drop of water with liquid water underneath it. That's the information from the Jack Hill zircons from Australia based on oxygen isotopes that they were formed from wet crustal rocks. So by that time, which is 4.3 billion years ago, there was a clement condition on the surface of our Earth. And so at first glance, we might say there's 270 million years to get from a calcium aluminum inclusion to a clement surface condition of the Earth. But actually, if you take into consideration the best age for the moon forming impact, which is our last giant impact that formed our Earth, we've only got 150 million years to go from magma ocean to clement surface conditions. Now, a number of decades ago, people thought that was barely enough time. We weren't going to make it. Something was wrong. But it actually turns out that that's plenty of time. And in fact, habitable terrestrial planets like the Earth probably go through multiple magma ocean and solidification to clement conditions cycles in their formation. And so with our Earth, this just forms an excellent starting place for the evolution of our current planet. Up until this point, up until the moon forming impact and the last giant magma ocean on our Earth, we were perhaps the victim of stochastic processes on many different scales. And so it's very hard to say what the clean starting condition is, but the magma ocean gives us a clean starting position for going forward. Now, these are results from a very recent paper by Nicolau, oh, that's interesting. There's a line cut off on underneath the Nicolau line where I also encouraged you to look at the work of many other people who've looked at the timing of the magma ocean. And so imagine that your name is there. So this recent paper is just looking at a wide variety of different compositions and densities of atmospheres on the young Earth. And you see the vertical axis is the depth of the magma ocean, with a completely solidified magma ocean being at 0, and then or at 1 really, and then the full magma ocean up at the top of the graph, and then time along the bottom. And so some magma oceans they found were solidified in as little as 1,000 or a couple of thousand years, and then the longest ones were at about 1 million or just over 1 million years. And that's in close agreement with my own work and with Kevin Zonley's work and with the really, really important formative work of Yutaka Abe and his lab, where they've done much of this work originally and inspired the rest of us to do this. And so it turns out that with plausible starting conditions on our Earth, a magma ocean can be completely solid in between thousands and 1 million or so years. And so 150 million years is much more time than we need to get from the moon forming impact to a clement condition where there could be water for zircons. So everything in the first, say, 200 million years of our solar system has become compressed and speeded up. Over the last couple of decades, all of us have discovered the information that shows that all those processes happened incredibly fast. And so we went through this rush of creating a planet and cooling it down, and then for the last 4.3 billion years, it's been the evolution from that starting point. Now, I want to talk a little bit about what happens when you solidify the magma ocean. And so this comes from work by Sonia Tiku and myself, but be sure to see Miyazaki and Koronaga's paper, Steph Brown's paper, Laura Schaefer's work on oxidation of the upper mantle, and others. And so this is just one exemplar. And in fact, the concept of this slide, which is that a solidifying magma ocean creates denser and denser cumulates as the cumulates are formed closer and closer to the surface, therefore gravitationally unstable and overturns. That goes back to Frank Spira and Paul Hess and Mark Parmentier. And so those are the references to go back to. In this slide, in this figure, we have radius of the Earth on the vertical axis, so the surface at the top, and then the density of the solidifying material that's solidifying out of the magma ocean on the horizontal axis. And so if you just look at the pale curve that says before overturn, you can see that, let's see, can I point, oh no, that's not right, go back. Can I go back? No, forward. Okay, that was back. Sorry, I've lost my laser pointer. It seems like it's different than what I had before. Forgive me. If you look at the pale before, thank you. Oh, it's the other one? There's two. It's okay.
It's working, but you don't see it.
It's, never mind. Okay, laser pointer does not work. Okay, so if you look at the pale before overturn curve, you'll see that since the cumulates, the solids falling out of the magma ocean, are forming from the bottom up to the top, the first cumulates are low density. They're high in magnesium, they're low in iron, they're expelling iron into the evolving magma ocean liquids. And then as solidification goes on, that curve moves to higher and higher densities as those solidifying minerals take in more and more iron. What this means is that the solidifying magma ocean cumulates are gravitationally unstable, and they wish to overturn in the solid state via Rayleigh-Taylor instabilities into that dark curve, which is the after overturn curve. And so a couple of things to note about this, one I'm going to mention at the end. Look at the tail end of that after overturn curve. That's very dense material. It's a very thin layer of extremely dense material. That material will also carry with it the bulk of the incompatible and radiogenic elements that were in the magma ocean. And so there's a very good chance that that deepest layer is still existing on the Earth today, hot from radiogenic elements, so compositionally dense that it cannot be re-entrained in thermal convection. And so that's an interesting aspect of perhaps the ultra-low velocity shear zones down there at the bottom. The other thing to really note about this is once this has overturned and multiple people have looked at this process, it's likely the primary part of it is likely to happen within 1 million years. It could start while solidification is still ongoing, but it's going to create a stable, non-convecting mantle to begin with. So after or during solidification, the mantle overturns to reach gravitational stability. Now, let's look at what happens with water. This is the same graph on the vertical axis, the radius of the Earth, and on the horizontal axis, instead of density, it's the amount of water in those solid cumulates. So this is water that is scavenged out of the magma ocean liquids by solidifying minerals, OHs, or waters held in voids, or defects, generally not hydrous minerals. It's very, very difficult to put enough water in a magma ocean to have hydrous minerals, but these are traces, and it turns out they matter in the end. And so again, that pale curve that you see at the top is water in the solidified magma ocean, because the upper mantle minerals both will accommodate more water and the liquids are more water rich by that time. And this is starting with as little as tens or even hundreds of parts per million of water. This is not wet in a sort of wet earth surface sense. This is just a trace of water. Now look at that blue vertical line. That's an estimate for the maximum amount of water that could be accommodated in the lower mantle of the Earth. So in bridgemite, in magnesia wustite. And so when those hydrous pre-overturn cumulates that you see in pale color at the top overturn into the deeper mantle, they have to pass through the transition zone and become lower mantle minerals. And as they do that, they by necessity expel their water, because the lower mantle will not accommodate water in those mineral forms. And so there's a hypothesis that we have that maybe overturning of a magma ocean can also flux the upper mantle with water, something that would only happen on a planet larger than Mars, where there was a lower mantle for this to happen to. Now, thermal convection only begins slowly after magma ocean solidification. This is work by Sarah Zaranek and Mark Parmentier. There are 3 time slices, and then the fourth The fourth square on the bottom right has time as its bottom axis. Now, if you look at the top left, you see the colors are actually density, and the densest material is at the top in the dark blue, and the least dense is at the bottom in the red. It's a simple linear density profile approximating the pre-overturn density profile that I talked about earlier. Now, the heat transfer boundary of note here is the top against the atmosphere and against space. And that material is able to become cold enough that through contraction based on the mineral's thermal expansivity, that material can become dense enough that it starts to sink downward. So then we're getting some thermal convection. But it reaches a point at which the dense cumulates beneath it no, I'm sorry, I really introduced this slide wrong. The densest material is at the bottom. This is post-overturn, forgive me. This is post-overturn with the light material at the top. So the densest stuff is red. So the blue material becomes more dense as it becomes cold. It begins to sink into the interior, but it can only sink until it reaches material of its own density. It's not going to sink through denser material. And so that convective mixing only goes down to the depth that the cold material matches the density of the cumulates where it is. And it takes a very long time for that material to mix. It can take tens or even 100 million years or more. And so this, we posit, is actually the starting point for the interior of the Earth. It is stably stratified. It's compositionally differentiated even within the silicate mantle. Thermal convection is slow to begin. There is a dense atmosphere above it. And so these are the conclusions with my little image to remind us of the compositionally stratified Earth, rapidly solidified in just 1,000 to 1,000,000 years or so. And so magma oceans solidify extremely fast and allow the planet to have a climate surface condition rapidly. They are compositionally differentiated and gravitationally stable. And so convection is suppressed in the beginning of the planet. The upper mantle is oxidized. This is really interesting work done by Laura Schaefer and done by group in Germany experimentally, looking at how the fractional crystallization of a magma ocean naturally drives its oxidation state from reducing, that is to say perhaps iron wustite at the core mantle boundary, to relatively oxidized in the upper mantle just through the process of fractional crystallization, not needing later accretionary impacts or a different kind of composition accreting to the Earth. That's a really formative, important piece of information about where our Earth started. And the deep, dense layer down there may persist to today. And so that is, to my mind, really the initial conditions of the Earth that are set by magma ocean processes, probably any terrestrial planet the same. With a deep atmosphere and water on the surface. And that atmosphere is not entirely erased by giant impacts nor by the late heavy bombardment. And so traces of that atmosphere are retained and then replenished by volcanism. And then finally, to point out questions that we need to answer going forward, what is the evolution of the core? So much new information about the core coming just in the last decade, just when I thought that I understood the core and I knew what was happening. So much more to learn about that. How does plate tectonics begin and evolve? This idea of drip magmatism, does that drip instabilities and delamination, is that the way plate tectonics begins? How can we tell? Is it inclusions from mantle minerals that tell us the timeline, or is there a much longer timeline? And then how does interior evolution affect the continents and the oceans? And so our colleagues who are going to follow in the talks right now are going to talk about both laboratory experiments and observations that we can make today that tell us about the evolution of the Earth from its early times, maybe from these initial conditions. Thank you very much.
Ladies and gentlemen, please welcome Bruce Buffett.
Good. I'm ready whenever you are. Well, my starting point for this talk is actually the key point that our initial condition for the planet is set by the processes of accretion and differentiation. The details of that initial state are actually quite uncertain. We still have gross uncertainties in what the initial state is, but there's quite a good likelihood that when the core was actually put into place, that it was substantially out of thermodynamic equilibrium with the surrounding mantle. And what that means is that chemistry can take place at the core mantle boundary, and that these reactions can potentially get incorporated into the mantle and give us signals that we can record. And this is kind of useful because it provides a probe that we can look back and find evidence for the evolution of the Earth really over geological time. So the evidence for disequilibrium comes from decades of experiments on the partitioning, element partitioning between silicate melts and metals. The goal of these exercises is to understand the experimental conditions that can account for the abundance of moderately siderophile elements that get left behind in the mantle. The emerging picture that has come from these sorts of studies is that the core last equilibrated with the mantle silicates in a deep magma ocean, perhaps pressures of 30 to 50 GPa and the corresponding liquidus temperatures. The idea here, at least in this particular story, is that once the metal ponds and descends into the core by diapirs, that the ability to exchange with the surrounding material is limited, and so that this is the imprint of the equilibrium and defines the composition of the core. There are, in fact, many different stories that could be told to explain these observations, and from my perspective, those different details and stories don't matter very much. After solidification, on the other hand, though, what we have is a core which is now against the mantle at a pressure which is much higher and at temperatures which were much higher than those that were experienced at the base of this deep magma ocean. And so the point is that the liquid metal in contact with the silicates is going to be substantially out of equilibrium. And so the expectation, based on these same partitioning experiments, our current knowledge is that you would expect the elements like FeO and SiO2 at the base of the mantle to be depleted and to be transferred into the core, and correspondingly then the abundance in the top of the core will be enriched in these light elements. Now we would expect a reactive zone at the base of the mantle to gradually proceed by diffusion slowly up into the overlying mantle. But this only has to proceed by a few tens of meters before the density anomaly associated with this reactive zone is sufficient that it actually allows gravitational instabilities. This layer will essentially rise up on timescales of several tens of years, or several tens of millions of years, excuse me. And the point, I guess, is even though that this is slow, operating over geological time, it's possible to process anywhere from a few tenths to a few percent of the mantle volume. And so this leads to the possibility that there could be geochemical signatures associated with this ongoing reactive process. Just to give you some examples, estimates of partition coefficients for nickel and cobalt are expected to decrease at the pressure and temperature conditions of the core mantle boundary. And what this means is that cobalt and nickel are slightly less siderophile. And so the expectation is that some of these elements, nickel and cobalt included, can actually return to the mantle. The partition coefficient for tungsten is less well known, but even if it was the same as the value in a deep magma ocean, the abundance of tungsten and its isotopic anomaly suggests that we could have a diffusive transfer of this anomaly back into the mantle, potentially consistent with observations recently reported by Rizzo and company. There are also interesting consequences for the dynamics of the core. We only need relatively small variations in the FeO content at the base of the mantle to produce fairly substantial density perturbations inside the core. Expectations based on local equilibrium calculations suggest that the density anomaly of the fluid in the core might be on the order of a part in 10 to the 4, whereas convective anomalies driving the flow, we think, in a normal dynamo situation might be 10 to the minus 6, 10 to the minus 7. So these are very, very large flows, and in fact, they may even be more important than the flows that we get with lateral variations in heat flow. So to sum up, the likelihood of chemical interactions with the core and the mantle, in my opinion, they're unavoidable. And what they create is an opportunity to probe back into the past, because the extent of these interactions are going to depend on the past and present states, and by interpreting these geochemical signatures and others, we'll be able to sort of learn something about those states in the past. Thanks very much.
Thank you, Bruce. Ladies and gentlemen, Jessica Irby.
I'm I'm going to take the next 5 minutes to convince you that using seismology, taking snapshots of Earth's interior today, we can say something useful and constructive and fundamental about the evolution of Earth's interior over the past 4.5 billion years. So what we can see first is an animation of seismograms propagating across the Earth. This is a simulation carried out for an earthquake that happened the end of last month. Waves travel slowly out across our planet. We can also see what a seismologist would record at the station nearest the Moscone Center here. Just across the Marin Headlands, we see seismic waves arriving with different amplitudes. We can measure the time it takes for these different waves to arrive, waves which are transmitted through the Earth, waves which reflect off interfaces in the Earth. And we can also look at the frequencies of Earth's whole planetary vibrations. Using these sorts of tools, we can discern important information about the complexities of Earth's interior. So let's start by seeing what seismology can see on an AGU centennial perspective. This is a discovery from early in AGU's history. In 1936, a seismologist called Inga Lehmann found a whole new layer of the Earth. She observed Earth's inner core, this central iron solid body. She did it using seismic waves. And we know that seismology in this case is seeing something which wasn't always there. The inner core is the product of secular cooling of our planet. And early in Earth's history, there was no inner core at all. We found it with seismology. In fact, we don't actually know how old the inner core is. The measurements that you would need to make to estimate inner core age are very challenging. But the inner core is probably of the order of 1 billion years or maybe 500 million years old. And with seismology, we can locate the inner core, but we can also learn much more. With seismology, we can measure the time it takes for waves to propagate through the inner core, and how these travel times vary as you transit different places of the inner core. You see maps with beautiful bright colors corresponding to where waves might be fast, where waves might be slow, where the travel time of a wave might actually be affected by the route it's taking. And with these seismological observations, we can go to modelers who make interesting, exciting, and varied models of the evolution of the core and say, maybe the core's evolution is really driven by the mantle outside it. Maybe the inner core is melting in some places and freezing in other places. Maybe the inner core is slowly sliding from one side to another, or maybe it's slowly spinning beneath the mantle. With the seismological observations, we can start to interrogate all of these different models of inner core structure. We can also take these seismic techniques up out of the inner core and into the mantle, and we can try and understand what seismology can tell us about mantle evolution over the past 4.5 billion years. Seismologists can make models of where waves travel more quickly and where waves travel more slowly. In the case of the models I'm showing you here, you can track subducting slabs, the remnants of plate tectonics, as those slabs descend through the mantle, sometimes going all the way to the bottom of the mantle, but sometimes stalling in the mid-mantle. We can also look at seismic models which show hot material rising from deep in the Earth. This hot material is associated with the phenomena of hotspots, associated with rising, maybe chemically distinct material. All of these observations are showing us the integrated results of 4.5 billion years of plate tectonics and 4.5 billion years of mantle convection. We can also look at very recent discoveries in the inner core. Here we're looking at seismic phases which travel through the entire planet, bounce on something on the far side, and travel all the way back. When we look at these sorts of signatures, we see energy arriving at unexpected times, telling us that there's lots of roughness on boundaries inside our mantle. What we can learn from this is that there's chemical heterogeneity present, and although we have circulation in our mantle, it's not perfect, it's somehow impaired, and the roughness and texture we can see are actually the product of billions of years of mantle circulation and plate tectonic evolution. So we're using seismology to probe the present-day structure of the Earth. And in the inner core, we're seeing the integrated product of all of the forces that have happened to the core through our planet's history. In the mantle, we're seeing the evidence of billions of years of mantle convection. And these observations can then be interpreted in the context of mineral physics, in the context of geodynamics, and in the context of geochemistry. Because if we want to understand Earth's evolution, it really has to be a multidisciplinary endeavor. Thank you.
Ladies and gentlemen, Hitoshi Kawakatsu.
Okay, I am a seismologist too. How does it start? Oh, okay. Plate tectonics is essential for life and habitability. Earth is the only planet that operates under plate tectonics, but we still don't know why. Earth's oceanic mantle is the only place where we can directly observe plate tectonics processes to find the answer. This is my homework for today. So seismology can offer you a best tool to study this, but Earth is uneven. Not only the distribution of seismic stations, but also seismic sources, which means earthquakes. So what can we do? So seismologists have realized the ocean waves can be a source, seismic sources. By observing noise wave field at two stations, we can extract a traveling wave from excited but at one station and observed at the other station. That means we have a way to convert seismic stations to the source. So if you have an array of network of stations like this, for all the observed seismic wave field, we can find the traveling waves between all the pair of stations. That means it would look like this. So this kind of traveling waves can give you the structure beneath the array. So this offers a new way to study the suboceanic mantle beneath the array using seismic earthquakes and noises, which covers wide frequency band. So ocean bottom seismology now at the stage, having 10 or 15 ocean bottom seismometers for a year or two enables us to resolve the suboceanic structure from the surface to the asthenospheric depth range down to 220 kilometers or 50 kilometers. So this is compared to the previous approaches like refraction survey, which just covers very shallow part, or global tomography, which has a large view but limited in details. We can now have a new way to observe the structure from the surface to the asthenosphere. It's I think, breakthrough in seismic observation or study of structure of the suboceanic mantle. So this has led us to propose a large-scale experiment in the ocean called Pacific Array to build an array of arrays in the Pacific, like this. And this was proposed about 5 years ago, but now evolved in reality. At least we have 5 arrays funded by agencies, and some of them have been already deployed. So which is quite evolving fast than I expected. So with this kind of arrays, probably in the next 5 years or so, we should be able to resolve one of the classical problems in plate tectonics, which is the enigma of seafloor flattening, shown like this. And with the, this kind of array technique, by delineating the structure of the asthenosphere in detail, you should be able to really give you the which proposed mechanism would be more appropriate. Okay, so there are much more happening in seismology in the ocean. For example, on the right top, this floating seismograph called Mermaid is complementary and very promising. With 1,000 of these floating seismographs, we can cover entire oceanic area within maybe 5 years or so, which would increase our ability to image deep Earth from the ocean. Also, fiber optic cable sensing is very promising because it can convert submarine telephone cables into seismometers. So this would be a new way of doing observation in the ocean. As to the sources, any disturbances in the ocean, like ocean waves, hurricanes, or weather bomb could be the source, as well as industrial exploration imaging technique, which can go now ultra deep down to 100-kilometer depth at the bottom of the oceanic lithosphere. So unraveling Earth's interior from the oceans is the way to go for the future with lots of challenges and opportunities. Thank you.
Ladies and gentlemen, Anne Devaya.
So good morning. In fact, as the planet is formed hot in a cold universe, its whole evolution is going to be through cooling. And because of the large temperature difference across its mantle, it's going to be conditioned by thermal convection patterns. So geodynamics is aiming, since the pioneering work of Holmes, to understand thermal convection and to decipher its evolution. Some question from the beginning is, for example, is it just cells with upwelling at the rifts, at the ridges, and downwellings at the subduction? Where do the plumes come from? How do they interact? And what type of thermal convection can produce plate tectonics? So if we look at a very simple mantle with a constant viscosity, so the intensity of convection depends on the Rayleigh number, which is the ratio of the engine of convection, thermal buoyancy, and to the viscous forces that oppose convection. So this Rayleigh number increases with the intensity of convection and with decreasing viscosity. For the mantle viscosity and the mantle system, the Rayleigh number is around 10 to 7, 10 to 8. And in fact, we are in a regime where we should expect plumes, but both hot and cold plumes. So it can explain hotspot by mantle plumes, but you cannot produce surface plate nor denser provinces at the bottom of the mantle. Now, if you introduce density heterogeneities, and we know that they exist, some patches with more iron or more crustal content, then you have an interplay between the density of chemical origin and of thermal origin. And in this case, by increasing the amount of denser material, you can drastically change the shape of convection, the shape of plumes. And so that can explain that we observe several types of hotspots, and so they would be produced by all this zoology of thermochemical plumes, but we can also have piles, denser piles, that could remain at the bottom of the mantle for billions of years. So, but how to make a plate? Well, you have to consider that the viscosity of the mantle depends very strongly on temperature. And so a cold temperature means a very high viscosity fluid. So it introduces an asymmetry between hot and cold currents that you can measure by the viscosity ratio. So if you increase the viscosity ratio, still having hot plumes, but your cold boundary is going to have less and less potential to flow. And so you're going to pass from cold plumes to cold cells and even to a cold plate that is not going to move anymore for really high viscosity ratio. This is exactly where the Earth is. So it's very easy to make a plate, but you don't break this plate, you don't make plate tectonics. So to break the plate, you really have to consider the full complex rheology of the Earth's material. So at cold temperature, we know it's brittle, we've got earthquakes. But this material is still flowing, creeping on the geological timescale at high temperature. in addition, you have a lithosphere that has a lot of heterogeneities and that has a texture that has been built in between, at length scales that are in between the grain, the building block of the mantle, and mantle convection scales of 1,000 kilometers. So it is possible to find analogs fluids in the lab, colloidal dispersions. And now if you run experiments, you get a plate on the surface, but this plate can break because of the brittleness of your material, especially. And so you can get one-sided subduction with only one plate going under its neighbor. And it can be induced by compression, but also by plumes. So large plume can come and break the lithosphere, then spread on it and push the denser lithosphere down, and so inducing subduction in several arcs around their rim. But the detail of the initiation really strongly depends on the rheology and how brittle it can get. So continuing the experiment, you can really get to continuous plate tectonics. Well, the movie is not working, where you have subduction, ridges, several plates can coexist, and you get plumes. So all this system, anyway, is always very strongly evolving through time. From a hot beginning and a hot magma ocean, a planet is going to undergo several regimes, and right now, if we look at the different planets of the solar system, we probably have different snapshots of those different regimes, from subduction and plumes to plate tectonic and plumes and to stagnant lid. So if we want to learn also on the history of our planet, it could be really interesting to look at other planets, what are they doing right now. So at the conclusion, I would say that as future challenge, what I see as the most burning one is really to understand the rheology and especially to consider the effect of texture at the mesoscale on the rheology that is going to be important to break a plate and to get plate tectonics. And then I think that the role of fluids or weak phases and melt is going to be extremely important, but for the moment it's not very well quantified. And then the experiments are also showing that there isn't only stagnant lid or plate tectonics regime. There is a lot more out there, and we really need to learn more about them. Thank you.
Ladies and gentlemen, Clint Conrad.
Hi there, I'm Clint Conrad from the University of Oslo, and the previous speakers talked about the history of the mantle from the very beginning, Lindy, to modern plate tectonics, and also talked about mantle dynamics from the very bottom to the very top, and I'm going to kind of link things together across all those scales, possibly. One thing that the last speaker talked about was she mentioned it briefly, the large, low, slow velocity provinces that are, and these are the two, if you look at seismic tomography, the two areas right beneath Africa and the Pacific, which have anomalously slow velocities and are thought to potentially be dense material that's chemically distinct from the rest of the mantle. And those are sitting at the bottom of the mantle, kind of beneath the convecting mantle, and the slabs seem to be sinking in the vicinity of them. This is a cross-section of the mantle through, showing seismic tomography through kind of an equatorial cross-section. You can see the slabs kind of on two sides and the low-velocity material on two sides above the two LSVPs. If you compute mantle flow for this type of configuration, you tend to have upwelling above the LSVPs and downwelling between them. And one question is, how has that flow pattern changed with time? One clue to this is the positioning of the plumes. The plumes tend to be coming up from the edges of these two LSVPs. And you can see their locations here. The primary plumes are producing intraplate volcanism tend to be on the edges of the LSVPs. And we think that the slabs are sinking in a ring around the LSVPs and pushing the flow towards the LSVPs, pushing the plume material towards the edge of the LSVPs where it then rises up. Going more towards the surface, this flow pattern, this large-scale flow pattern, should drive the plate motions. It should be, in fact, the plate motions are the surface expression of this flow. And so one thing we've done is we've basically taken the spherical harmonic decomposition of the plate motions and figured out where the kind of a net divergence poles are, and they're the two poles, that I'm showing here with the minus signs. And there's one above the Africa and one above the Pacific LSVP, and it makes sense that you'd expect to see divergence in these areas, divergence of plate motions, if the mantle is upwelling in these, beneath these regions. Now what's really interesting is that, see, now we're using plate tectonics to kind of infer the pattern of mantle flow beneath, at least on long scales, and we can do that in the past because we have tectonic reconstructions of past plate motions. So we can do that and calculate those same poles, and what you find is that the divergence poles tend to lie over the two LSVPs, and they're stable there for at least the last 250 million years, for which we have plate tectonic reconstructions. So the colors here show the locations of those divergence poles in the minuses as a function of time, and time indicates the color. And then the positive poles are the locations of the convergence poles where the center of subduction would be. Right now we're in an east-west configuration, but in the past it's been north-south. And so what we think is that if you have upwelling steady above the LSVPs, and then the locus of subduction kind of pivots around those two central stable areas. So this is the picture of the mantle that at least we have for the present day, I think, is that we have subduction in a ring around the two LSVPs, and the two LSVPs are relatively stable, produce upwellings. Now this flow is going to drive the plume, the lower boundary material, towards the edge of the LSVP and push it up against the dense LSVP, shown in the yellow color there. This is a new model by Bjorn Hain, a grad student working with me, who showed that you can get pulses of plumes. You can see the pulse, the next plume coming against the LSVP, and then the plume rises from the edge of the LSVP. And what a question is, at least, is how long has this convection pattern been stable? The surface plate motion suggests that it might have been stable for hundreds of millions of years, and a question is how long in the past could it have been stable? Thank you.
So I think we should all thank the speakers because they did a great job with their very stimulating presentations. And we do have time for discussion, so if you have any question you want to ask to any of our speakers, or just a broad question that you think they might answer, you're very welcome to.
Hello, thanks for those talks. That was really nice. I have a question for Lindy, actually, about the whole mantle overturn. I was always curious about why a gravitationally unstably stratified solid mantle crystallizing from a magma ocean would wait to overturn until after crystallization has finished. And that seems to be a really important part of the story. And a secondary part, a follow-up question to that is, in that scenario, the mantle's at the solidus, right, the solids. So you would have decompression melting accompanying the overturn as well. Have you thought about that?
Thank you. Hey, John. The overturning question, the time scale of overturn has been solved for analytically, and it's been looked at through numerical modeling, and it's dependent upon the slope of the increase of density. And so in the beginning, in the beginning of solidification, the cumulates are becoming denser, but at a slow rate. And then it's also dependent upon the inverse of the square of the thickness. And so, so the thicker the layer is that's unstable, the faster the overturning initiation, and the greater the density, the faster. And so timescales of overturning don't become faster than timescales for solidification until late in magma ocean solidification for the moon. For the Earth. On the moon, we've actually done those calculations for the hot material rising up, and it will remelt, and it's consistent with potentially with the high MG suite. And so both of your things are exactly key questions to this whole process.
Okay, do we have any other question?
Yeah, maybe just a follow-up on the same topic. It seems to me that the temperature also matters for this destabilization. In fact, if you take, if the temperature of the solid follows the solidus, that depends on composition, you would expect a very steep temperature gradient as well. So I think that could help actually destabilize much faster than maybe getting to the end.
Yes, Sasha Solomatov did I think the first work on the importance of temperature along the solidus for the overturning, and it does encourage overturning, and it's included in our models. That's absolutely true.
Okay, I have one more question actually that I want to ask is, in the last presentation, for instance, we saw that maybe the LLSVPs were driving how mantle convection is happening now, and I wonder, do we have any idea how long the D double prime layer and LLSVPs have existed?
Oh, is this on? Yeah. I maybe can't speak for the D double prime layer, but the LSVPs, presumably, maybe one of the other speakers could talk about this, but presumably they formed as a result of either the primordial conditions, the initial overturn, or it's a accumulation of basalt from subduction that gets accumulated down at the bottom of the mantle. And so they either formed initially or grew slowly over time, but they seem to be thermochemical piles that are stable down there now. It is a question of if they move around, get pushed by the flow or not, and they seem to kind of organize the large-scale flow pattern of mantle convection, and in a way that is producing the pattern we see now, and it's a question of how that's changed in the past.
So this is a place where we would hope that seismology with its current day snapshots could help us. At the moment, seismology is using a few different techniques, the frequencies of whole planet vibrations, and a new method called tidal tomography to try and work out if these large low shear velocity provinces that we see, if as well as being slow, they're dense, or as well as being slow, they're buoyant. And if they're buoyant, we would expect them maybe to be more of the transient end member. If they're dense, we would say that maybe they're more of the primordial end member that Clint just mentioned. This is a place where tomographers are working really, really hard, but right now, some of the seismology results say that they're dense, and some of the seismology results say that they're buoyant. So I think this is a place where if we come back not in centennial year, but maybe in a few more years, we might have a slightly more useful answer to share with our colleagues.
Okay, I think it's time to close the session, so we can go discuss in the discussion area over there, and thank the speakers again.